the speaker approval. Now, today we are very happy to have Dr. Tai-Yue Li to give a presentation on the application of quantum machine learning in MRI data. Now, in fact, this is one of the three consecutive talks we're going to have in this summer time. We will have two more speakers coming up. One is Louis Chen and Professor Sukis Molo. We will schedule the talk and let you know as soon as possible. And you can look up at this table over here, and here are the title of this series of talk. There is quantum computing, bridging advanced computation and practical applications. So let me give you a brief introduction of our speaker today, Dr. Tai-Yue Li. He's graduated with a PhD degree in physics from National Donghua University. Currently, he is a postdoctoral researcher at the National Synchrotron Radiation Research Center, NSRRC. His primary research areas include the application of deep learning in X-ray imaging and accelerating large-scale quantum computation. He specialized in using quantum machine learning algorithm to tackle biomedical problems. He served as an invited speaker in various quantum computing talks, in particular on the use of Qiskit and NVIDIA CUDA-Q in solving real-world problems. He won a first prize in the IBM Qiskit Hackathon 2021, and coaching winning teams at IBM Qiskit Hackathon helped by NTU IBM Q Center. So without further delay, so let me pass my microphone to Dr. Li. Okay, Dr. Li, could you share your screen?
Okay.
Go ahead.
Wait a minute.
Yes, okay.
Okay. Can you see my screen?
Yes, yes.
Okay.
Okay, so go ahead. Okay.
Okay. Hello, everyone. My name is Tai-Yue Li. I'm a postdoc researcher in NSRC. I'm very glad to be invited to share my work in the field of quantum computation. Today, I will present the topic application of quantum machine learning in MRI data, which was a small project I work on IBM QUAMP 2022. Okay, there is my outline. I will do some introduction about MRI and the structure MRI image and functional MRI images, and the Austin dataset with functional MRI data. And next, I will talk about autism detection with machine learning and deep learning. And next is autism detection with quantum machine learning. The final, I will talk about toward large scale and accelerated quantum computing simulation. Okay. Magnetic resonance image MRI is a medical imaging technology based on the principle of nuclear magnetic resonance. It is a primary use of diagnostic image in medicine. So you can see in this figure, this is a MRI device, and some person or someone will put in the device, and in this device, they will apply a magnetic field. So you can see in the center, in the if you without the magnetic field, the atom will moving, and if you apply a magnetic field, the atom will have some order stable, and then you input a RF signal, it will make the atom resonance, and we can get a signal output. So we can use the Fourier transform this from this signal to get a MRI image. This is the MRI principle, and the structured MRI image is a common MRI image. It's a 3D image. So in this image, it can provide some information about the shape, size, and some structure of our brain. But one main problem is we cannot get the functional connectivity of the brain. So you can see here, uh, the structure MRI image can catch the 3D. For example, it can get a 2D slice image, and one layer by layer, and we can compile those 2D slice image into the 3D images. Another data set is a functional MRI image. The functional MRI image is a 4D image, and one more dimension is for the time series data. For example, we can see that we can first we can get the structure MRI data, and next we can fix the XYZ place, and we can catch the blind signal. We can catch the blind signal to catch the functional connectivity of the brain. Yeah, because in our blood, the blood flow goes through. So we can, if we are doing some in our brain, if our brain some part of our brain some working, and the blood, the oxygen and the blood will some changing. So we can catch the signal from the blood signal. For example, the left-hand side is a structure MRI 3D image, and then we can separate the brain image to a small part. For example, 1, 2, 3, and then we can detect the blood flow over time series, so we can get a blood signal. You can see the figure B here, and this signal will represent some functional connectivity with brain. And another data is a resisting state functional MRI image. Resisting state is that for our common think is that if we are moving, or we are do some we are moving something like that, and our brain will pass through a signal to control our hand or leg, something. So some normal research, they use the moving and catch the brain signal, but this in this data is different. It is without text. In conjunction to the traditional text-based approach, resting state study observe the brain in the absence of over text performances or simulation. But some those study, like mental disease like asthma, ADHD, and depression, some like this kind of mental disease is undependent with the text. So we can use the resting state functional MRI image to catch the brain signal. Here is an example. We use the autism data set with the functional MRI data, and autism spectrum disorder (ASD) emerge early life and are generally associated with lifelong disability, and ASD affect around 1% of the population, and it characterized by difficult in social interaction, communication, impairment, and narrow responsibility pattern of the interest and behavior. ASD is characterized by automation of the functional connectivity of the whole brain instead of some local brain abnormality. Functional connectivity can be kept when patients of performance special task, or when a patient is in a resting or task negative state. So so many work they use the machine learning or deep learning method to detect the autism. So here is a process, a pipeline to compare the machine learning method and the deep learning method. In the deep learning method and in the machine learning method, the input data will first get the feature extraction, and next they train the model to do the classification, and then they get a result. And for the deep learning method, they use the neural network-based model to represent the a nonlinear mapping from input to output result. So the model combined with the feature extract and classification. And those two methods need you can see in the right hand side this curve. The x-axis is training data size. The y-axis is performance. So we can see that both of those two model they will show some high performance in higher data size. But in the fMRI data, we got the autism data is we cannot get so many autism data because the data is not easy to get. So one mention is that if our data size is not that huge, can we get a better performance? This is the main thinking. So one solution is that we use the quantum machine learning to solve that problem, because quantum machine learning can provide more nonlinear mapping from data to quantum feature space. Here is one of the popular method in quantum machine learning is a quantum enhanced SVM. In QSVN, which means QSVN, in this QSVN method, for example, if we have two data, x1 and x2, and we can map those two data into quantum kernels, quantum circuit here, and then we can map those two data into the quantum feature space, and then we can catch the similarity of those x1, those two data x1 and x2 in the quantum feature space. And finally, we can input the quantum kernel matrix to do the classification. And the quantum circuit is the main part of the quantum enhanced method. They can map the classical data into a more nonlinear quantum feature space. And the second method is the hybrid quantum neural network. It's a neural network combined with the quantum circuit. The workflow is that we can input a data set into the neural network, maybe convolution network or just neural network. And the next we can connect the last layer into a new quantum circuit, and then we can do the measurement and we get a result. And then this is the second method of the quantum machine learning. And go back to the autism detection. We select the autism fMRI open dataset, which is from autism brain image data exchanging, ABIDE. And in this dataset, we have 539 individual autism data and 573 typical control. And those data, because the autism fMRI data is hard to get, so those data actually is 20 different research sites. They combine their data together. So we can see that our data is a 4-dimension fMRI image data. 3-dimension is for the structure, and one more dimensional is time series blood signal data here. So we have two ways can do. One way is we do the feature extract. We can convert the 4-dimensional fMRI image data, convert to the 2-dimensional, 1-dimensional features, and the data is the x-axis is the number of feature, is 2016 features, and the y-axis is the number of data. For example, in this case is 1,000 12 data, and then we input the data into the SVN and QSVN because we want to compare with quantum enhanced and without quantum enhanced, which performance is good. And the second method is we just input the three-dimensional data. In first we use the summary. We can summarize the blood signal into the three-dimensional, so we can get the three-dimensional uh, blood signal data. And then we just input the three-dimensional image into the 3D convolution neural network and the 3D quantum convolution neural network. And in this way, we also want to compare with quantum and without quantum, the performance of the quantum enhanced. Here is our result. This is the first method. The first method, we compare the SVN and QSVN. So first, we do the data preprocessing. We convert 4D fMRI image to the one-dimensional image with 216 features and 871 data. And then we do the PCA principal components to reduce the dimensional of the feature. And then we train the data. We use the QSVN to train the data, and then we get a result. So you can see that this figure is the SVN's result. So the x-axis is the number of qubits, which means number of features, and the y-axis is the accuracy. So we can see the red line is the training accuracy. The blue line is the testing accuracy. So we can see that the maxima is near 90%, the training accuracy, but the testing accuracy is not really good. It's near 60 percentage. And we also can see the QSVM result in this figure. The x-axis also the number of qubits, but in this algorithm we cannot compute higher than 24 qubits. They have some memory bound in this part, so we can just get the number of qubits from 2 to 24 here. So we can see that different with the SVM, the training accuracy, they will quick go to high near 100% accuracy, but the testing accuracy is not really good. The maxima is 55 percentage is not really good. So in this case, we found that quantum enhanced maybe provide training more successful, but in the testing data set is not really good. They have some overfitting behavior in this case. And here is the method 2. So the similar pipeline, we input the 3D data, and we produce a normalization, and we train a 3D QCNN or CNN model. Here is the figure shows that the 3D data will input a 3D convolution neural network here, and then we input the last year's parameter into the quantum circuit, and then we get the result. Here is our result. The left-hand side is the 3D CNN result, and left-hand side is a quantum enhanced 3D CNN result. So we can see that their performance looks similar. Just the train data, the training accuracy is near 88%, and the testing accuracy is near 55 or 60. Yeah. And then both of those two methods, we can see that the classical method shows the more robust performance in the testing data, but quantum enhanced the result have more overfitting problem. So this is our small conclusion. Our small conclusion is that in the training data set, the quantum can very quick to get a high accuracy, but they have some more overfitting. And for the classical method, in the training data set, they may not perform well, but the overfitting result is less. So so I think the main problem is that how to use the quantum enhance, because we just input the data into the quantum circuit, and how that quantum circuit work is the main problem. So I think in the future work, we can design more new quantum circuit structure to fix that problem. And the next, we can change the training architecture here, because I mentioned that so many work they have some good structure about a quantum machine learning algorithm. So maybe we can use that different model. And then the last part I want to talk about toward large scale and accelerated quantum computing simulations. Because in currently the real world quantum computer, the qubit number is not really large. Now the largest quantum qubit number of a real quantum computer is from IBM. They built 1,121 qubits, but one problem is that their result can get some noise and get some error. And the next, the cost of the real hardware quantum computer is very high. We cannot use that. We are hard to use that part of device to work on quantum machine learning. So one solution is that we can use the simulator. We can use the classical computer to simulate quantum computations. there have two main simulation method. One is the step vector simulation, and the other is the tensor network simulation. The step vector simulation is a gate-based evaluation of the quantum computer. So, for example, here is the quantum circuit, and we can convert that quantum circuit into a series of matrix calculations. But this method is the more common method of the quantum computer simulation. But it have some two main problem. One main problem is that they require the 2 power n qubit vector state memory. It have some memory bound. So for example, if we need to calculate the 100 qubit circuit, we need 2 power 100 memories to calculate that quantum circuit. And the other problem is the running time. The running time will get very huge when the qubit number increase. Now, I think the limitation use state vector simulation in supercomputer, the maxima is we cannot go higher than 50 qubits on a supercomputer. So this is this method's limitation. And then the second method is a state vector is a tensor networks, and the tensor networks is a very powerful method. He will convert in the quantum circuit. We can convert the quantum gate into a series of matrix, and then the tensor network method, they will find a optimize calculation path and reduce the cost of the computation. So we no need to that huge memory require, and then the runtime will reduce, and this method will reduce large of runtime, so it can calculate more qubits. So here is the information shows that use tensor network method, we can simulate 100 or 1,000 qubits of quantum circuits. Here is the roadmap from NVIDIA. You can see that the x-axis is the number of qubits, and the y-axis is the circuit depth. So we can see that in real quantum computer QPUs, the limitations is that they cannot calculate more than 128. I think now it cannot. It can go to here 1024, but the circuit depth it cannot more than hundreds. Yeah, and if you use the state vector simulation, you can see that we can simulate very dense quantum very deep circuit depth, but the limitation is the number of qubits. We cannot get more than 50 qubits. They have some memory bound on supercomputer here. And that one, and you can see that if we use the tensor network simulation, we can simulate more near 32,000 qubits, very large qubits number. But tensor network also have a limitation. We cannot simulate a so deep quantum circuit. So one work is that if one tips is that if we create a quantum circuit, they are not so deep, but it performs well on some data set, so we can simulate very large scale quantum simulation. So here I will focus on tensor network this method. Um, NVIDIA, they create a CUDA quantum, quantum SDK, and that SDK is a quantum computer simulation library. They include both of state vector simulation and tensor network simulation, and then they can use the multi-GPU, multi-node to do the calculation. So for the tensor network simulation, here is the pipeline. We can convert a question, a problem, or a quantum algorithm into a quantum circuit. And we also can convert that quantum circuit into a tensor network the representation. And next, we can use the cuTensorNet, this library, to do the calculation. So when we convert the quantum circuit to the tensor network here, and first they can do some simplification, and next they will find the best path, that path which has the last cost of the calculation. And the next, they can input the data to the GPU to do the contraction and then get the result. Here is the example. We use this circuit to do the image classification on mixed data set. This data set have 1,000 data with 884 features. Here is the example, number 7 and the number 9, the image. And we convert this image. This image size is 28 by 28. We convert that image to the 7,084 features, and we map into this circuit. So you can see the data. We compare the different simulation method. The black line is the state vector simulation for one circuit. So you can see that the x-axis is the number of qubits. We cannot go higher than 35 qubits. So you can see that up to 20 circuits, the rounding time will go up, huge go up. And here has a memory bound in the 35 qubit. But if we use the cuTensor network, this method, we can simulate up to 784 qubits, and the running time just a few seconds. And if you use the passive reuse method, like the green line, you just lower than 1 second. So the tensor network simulation is more powerful in this case. And here is the result of the classification of number 9 and 7. So we can see that when we increase the number of qubits, the classification accuracy will have some interesting behavior in here. They will increase, but they have some. They will get to the maximum accuracy at 128 qubits, and the next they have a sharp bending when increase of the qubits, and that you can see that this result is just one quantum circuit. If we increase the number of data, we need more calculation time. So one method is we can use the multi-GPU multi-node to separate the data to do the parallel computation. So here is the result of the parallel computation of the cool tensor network. So you can see that we increase the number of GPUs, and we use the same data size and same number of qubits. So they will be faster, more linear, reduce the runtime. So if we use the A GPUs, we can reduce the running time from 8,000 seconds to near 1,000 seconds. So so this tool is very powerful, and we also do some benchmark here. You can see that the x-axis is the number of qubit, and the y-axis is the number of data size. So we in that circuit, we can use the tensor network simulation to simulate near 20,000 data of qubits, and near 12,000 of data size. So the sum point here is the sum application requirement. So you can see that the green point is lower cost task, and the orange point is median cost task, and the red point is the higher cost data size. So you can see that we use the purple bar to separate the running time, and you can see here is 1 year, and 1 month, and 1 week, 1 day, 1 hour, and 1 minute. So you can see that the different tasks they require the running time is different. So it means that we in tensor network method, we can apply more larger application on use tensor network simulations. Yeah. So yeah. So thanks everyone for my talk. Thanks.
Oh, okay. Can you hear me?
Yes.
Yes. Okay. Thank you, Tai-Yue. Okay, for the nice presentation. Okay. Yes, the tensor network SDK package is really a powerful package for doing quantum circuit simulation.
Yeah.
Yes. Okay.
Yeah. Really.
Okay. So let me see if the audience have any question. Then you can open your microphone. Right.
Okay, that's
Yes. Go ahead.
okay. I do have questions regarding your data sets. So your data sets, your input data sets is only from the brain MRI. Is it true?
Yes, but before input in the model, I do some data preprocessing.
Okay, because this is MRI, right? Usually they have their own layer from the layer top until final slice, like the lower part. So is it all of it you are using the full MRI brain scan, or only certain part as input?
Yes, because they already have some work on the feature extraction, so I just follow that method. So maybe the input data is not the original
Okay.
data.
Okay. Yeah, I just like wants to know that which part of the brain they are used for this input, because a lot of part of the brain we can use, right?
Yes.
Like from the
Yes.
top one until like the brain stem we also can use, but I don't know which one this one, which brain.
Oh, you ask this figure, right?
Yeah, I'm
This
yeah,
time
I'm seeing that
series.
figure. Yeah.
Okay. They will do the average. They will
Okay.
average the intensity. So they will combine different time data into one 3D data.
So it's also using the programs to combine or
Yes,
to like
yes,
filter. Oh, okay, I see.
yes. This data, this open data data set, they provide some method or code to do that part.
I see. Okay. Yeah, I do understand right now. Okay, thank you very much.
Thanks.
Okay, all right, yes. Dr. Esler is my former PhD student in my department. He just graduated and then doing his postdoc at the Hualien Hospital now. He used to study physical therapy, so that may have something. The functional MRI may be related to what he did in the past, right?
Yeah,
Okay.
that's why I just want to know. I mean, after you've done this research, which part of the brains is the most important feature that we have to consider for the autisms in this case? Do you know which part is it? Maybe like left part of the brain, or maybe in the front brain, or which part of the brain?
Yeah, but as Dr. Lee said, it's overall average intensity map, is that right?
Yeah, that's the
Yes.
case. Yeah, that's why we don't know right now.
Okay, so yeah, that's why we don't know. Okay. Okay, so
That
let me
needs the biology background. They do that part.
yeah.
They study
Okay.
on that part.
Makes sense. Yeah.
So if they do the average, then they could not have the functional connectivity information. They don't.
I research some paper. They do some special calculation on that part, and they can get more higher performance accuracy result. So I think that is the important part.
Okay. So here, let me follow up this slide. Say the third line from the top. You said 539 individuals with autism and 573 typical control from 20 different research sites.
Right.
So they make the measurement at 20 different location.
Yes.
But then they average out the overall intensity.
No, they combine their data, and each brain they one data they do the average.
So which each individual they treat it as a one single data point.
Yes.
Oh, so okay. Now another thing is about the three-dimensional CNN. So
Yes.
the three-dimensional is essentially the same as the handwriting digit. That is a two-dimensional image.
Similar
Similar.
structure, just
Okay.
one more dimension.
Okay, so they also have to go through the so-called the sliding window, and then
Yes.
do
3D convolution
yeah
and
they
the
will
3D
do.
pooling. Yes.
Okay, so it just have an additional dimension,
Yes.
and I would expect with a higher dimension, with one more dimension, the classification performance is going to be lower.
Yeah, some research show this behavior, and actually I see some research they do some they get some parameter inside the kernel, and they tune that parameter and make the result better. Yeah,
Okay.
some paper shows that. So we didn't know, but this is a reason why the QCNN they will not go high qubit, because they found that when increase of the qubits, the performance will not very good. It's
Now,
strange problem. Yeah,
with
we don't know
more
why.
cubed. Now, going back to the slide on the 3D CNN. Yeah, the one before. Yeah, okay. Now, for the convolution neural net, uh, they also have a lot of parameters, right? How many layers you use, and how large is the convolution doing. So how you pick this parameter? How can you know whether the parameter you're picking is a optimal set or not?
I follow the previous CNN work. I use the same same parameter of that neural network, and I just change the last layer into quantum circuit, just like that.
Okay. Also, you reference to one of the published work, and use the same sets of
Yes,
parameters
yes,
in your study.
yes.
Okay. Now, what about in the quantum part? Do you try a different, say, circuit there for introduce entanglement, like linear entanglement, such kind of possibility?
Uh, I didn't do that part. But yeah, I think maybe we can get better performance. But I didn't do that part. Yeah.
Okay, so for the quantum part, you make your own choice of parameters.
Yes.
Okay, all right. Now, another question is about in the stay vector and tensor network graph you show. With the stay vector, they can only stimulate up to yes, this one. So you see on the right hand bottom tensor net, there is a point, a square that is max cut.
Oh, right.
Yeah. Is this a real study or it's just
Real study. Some publish work, then
Oh.
they can go large scale.
Oh, okay. So they this is a real study. They study the large scale max cut problem using tensor network
Yes.
utility.
Yes. I remember that paper is from NVIDIA. So
Oh.
they use the supercomputer to do the benchmark.
Okay. Okay. Yeah. So they use the supercomputer to and with the help of TensorNet, they do the quantum circuit simulation for large scale
Right.
graph problem.
Yes. They
Okay.
can. I remember the maximum qubit is near 5,000. Yeah, 5,000.
Okay.
Maybe this point. Maybe.
Okay. Yeah. Okay. And then what about RQC? What is a RQC M40? What kind of a problem is it?
I remember this problem is published from Google. I remember they publish one paper say they got the quantum advantage, and they use one algorithm to do the benchmark. The RQC I think is the last benchmark.
Okay. Now, there's also another slide where you show the number of qubit goes up to 20,000. Is that right?
20,000.
Yeah.
Oh, this one.
Oh, yeah.
Right.
So this is also this 20,000. Is it also a result from using TensorNet?
Yes, we use the 800 GPU.
800 GPU.
H100.
800. Oh, 800.
Yeah, yeah. At that time, the Pika he give a chance to run our code on one node DGX. That DGX have eight hundred H100.
Okay.
Yeah.
Okay.
So
So
this data is from that part.
okay. So this figure is a result of you and your team member result.
Yes, right.
Oh, okay. I see.
Yeah,
Yeah,
it's promising. Yeah, yeah, because we can get to 2,000, the
yeah.
number of qubit and the data size, we can get to the 12,000. Yeah,
Oh,
it's
okay.
really promising. So,
Oh, I see.
yeah, we I think we will follow this work.
Okay.
Yeah.
Hey, but you see on the right-hand top corner, it takes the supercomputer 1 year to run. So they have you have your team have such a large amount of resources.
No. Actually, we just get two data. One, we first we fix the number of data. and we increase the number of qubit, and we got the data line here. And then next we fix the number of qubit. We increase the data size here. So we use those two lines to get this for data. So I think this part is we calculate by our calculate result.
So you mean you do extrapolation from something smaller, extrapolate to?
Yes.
Oh, okay, I see.
Because we cannot have.
Yeah, so I just wonder how it takes 1 year.
No. No.
Okay.
Yeah. After actually we just have 1 week can use that device.
Okay,
Yes.
I see. Okay, okay, I think that maybe some of other the audience have a question. Sorry, I have raised so many questions. So okay, so let me see if the audience have any question. Yes, like from Makila, Anita.
Hello, Professor Li.
Yes, yeah, go ahead. Okay,
Thank you. Okay, Dr. Li, I'm Alex, and long time no see.
Hi.
Hi. Today you made a great speech. Very nice. And I want to like to ask. I guess we know the expandable AI is an important topic right now. So do you have some research related with the expandable quantum AI?
I know this part, but I didn't start to work on that. I think maybe we can learn this part from AI, and next we input loss method in quantum. I think is a good way to do that.
Yeah, and Professor Taylor, do you have an interesting in this topic?
I didn't work on explainable AI, but so do they have a more precise meaning of what do they mean by explainable? Do you give a more?
I understand, because for example, the image, for the case of image, for example, if we want to do the classification, right? So if we train one model, and we can input some image, and we can we input we train the model maybe like a convolutional neural network, right? And the end of that neural network, the last layer, we can take out that layer to see which feature is important. So if for example 7 and 9, those two figure input that model, and we can take out the last layer of that model. Maybe we can see some feature in that part, and I think some so-called explainable, maybe they learned this kind of structure is 7, and this kind of structure is 9, something like that. Some explainable feature in the neural network.
Yeah,
is right.
yeah, but then for the last layer, okay, before I mean those are the hidden layer before the output. Now what you can have is only the weight, right? The weighting factor, because all the neural net is just doing approximate a function, try to as close as possible as the input. So you try to minimize, say, the cause function or the loss function, whether it depends on the mean square, diff error, or whatever. But then you only have a weighting, like the coefficient for each node, okay, on the neural net. So from that, then if you have a positive coefficient or negative coefficient, then what I can think is with a large, if you normalize it, everything within something, say between -1 or 1, then you can tell the difference between whether certain features have more weighting and some other feature has a negative weighting factor. Then, but those features, as Tai-Yue said, from by investigating the last the layer, they may give you some overall idea about which feature is has a more heavy weight and some with a positive weight and some with a negative weight. So is this something that Yun Chen you are thinking about?
Professor, and let me try to explain a little bit about what I'm knowing just right now. Okay, the explainable AI. First example is to explain the convolution networks, and that is means before that the convolution CNN convolution networks neural networks is just like a black box, right? We just can find the input and the progress and the result, and the result just the weight and the bias in the neural networks, right? So that one way is to try to visualization the CNN during the progress to calculate the trend data set and the in the progress. And then another I see is they find long time ago the some biotechnology teams, they research the reaction between cats and the vertical and the horizontal line, right? And that team has got the Nobel Prize in the biochemistry field, and that is means in the picture in the PPT here we can saw the 7 and the 9. Yeah, but the computer and the convolution networks, they don't understand first. But when use the XAI, that mean the short term of the expandable AI, they find that the convolutional neural network is to find a group of the features, not only the vertical white line and the vertical white line, and there is between the number 7 and the number 9, they have a bunch of a small group of features. For example, maybe they have a 45-degree line, a diagonal. That is the explain and the inference process during the CNN, and then that is be announced by some papers there. So I mean, they maybe have some many ways to explain the behavior, the AI behavior, the CNN behavior, and maybe also the quantum computing behavior. Then in the different method or different explanation, then it can help human much more understanding what's the machine thinking. Okay, so we can cooperate the machine learning and cooperate with the human learning. Okay, just that's all. Okay, thank you.
Okay, yeah. Following up on what you said, I mean, yeah, for the computer, they divide this 2D image into some pixels, right? Pixel, yeah. So how to tell the difference between 7 and 9? They would have I don't know, different the gray level or pixel level, and by yeah, that might be related to what I said, right? Because you have those features. I don't know exactly how the CNN work together. They all have input those 7 and 84 features altogether into the CNN for training. So it's Yun Chen, Alex, what you said is among these 784 features, you can to pick up some of the important features.
Yes, and the 784 is equal to 28 multiple 28, right? So that is means we need to the dimension, we need to down dimensional. This is a 2D picture, right? But when we input it to the CNN, we must make it become a one dimension string. That is the first criteria when we use the CNN. So we change or we say we transform the 28 multiple 28 pixel. Or that means it changed to transfer it to the 784 pixels, just like a very long series line, and the input to the CNN. And in another traditional way, that means if we just know if we just assume this black and white picture just only have two features. One is a vertical white line, and the second is the horizontal white line, and the third is the black. Or third is nothing, just black. And then we can distinguish in the statistical way, right? We can calculate the picture 7. They have how many vertical or how many horizontal line. Then maybe the diagonal, I mean the 45 degrees line, just like a half of half. Maybe we can give him a weight at maybe just a 0.5. Yeah, and that is a traditional statistical way to calculate the feature of this picture, 7 of this picture. And we can get an account, how many vertical line, how many horizontal line, right? But in CNN it's different. CNN, they explain that they really use some graphical way to handle this graphical. Even you just input is a one dimension, yeah. And they will by the connect to the full connection neural networks and the other poolings and especially how do we say that we have a small of the window, and that will during the process will to move under the left after to the on the right corner, right? That is the CNN assess the progress there, and that is will be extract the some kind of group of new feature because the sliding window progress, and then that will to generate the second matrix of the original picture, and then we can do this progress many times. Then we can get the stable training data, or the final eigenvalue, or say the final picture. And that is a very strange way. It's different from the statistical way. And then also, I have watched some paper. It's called, if we use this kind of CNN-like method, we will use a sliding window to through the new pictures. Then they will and I will get the result is very like an fly's view. You know, we people just only have one eye, right? We only just have two eyes. No. But the fly, the mosquito or the fly, they have yeah, many eyes. And then that kind of situation is very close that. I have saw that picture in another paper. Yeah. And as I know, just that. Okay. Thank you.
Yeah, I don't have any study on explainable AI, but it will be interesting. Yeah, Alex, you have come up some. We will paper on explain AI, and yeah, post it, and I'll align groups to that I may have time to read it and see what is the current status of this area. Yeah, I do know next year Asia University is going to host an international conference on XAI in the healthcare and medicine. Yeah, next year. Yeah, international conference on explainable. Yeah, AI. Yes. Any comment, Tai-Yue? Oh, explainable AI.
I think it's interesting. Yeah.
Okay, all right. I think it's almost time we to have to close this presentation. So so let me say thanks to Dr. Li again for the nice presentation.
Thanks.
Okay.
Thanks.
Yes, thank you for your presentation. And after the talk, I will have asked you about whether you can make the presentation material or the video publicly available.
Oh, okay.
Okay. Okay, thanks again. All right, bye.
Bye-bye.
Yeah, bye.
Bye bye.
Bye.